Welcome to Module 3. Hard to believe we're almost a third of the way through the term. One of our goals is to explain changes in behavior over time, specifically levels, trends, and variability. The definition of these can be found here, but they'll be reviewed in future modules as well. Data collection and visual representation of those data is a key pillar of the field of behavior analysis. Rather than simply writing down numerical data and basing decisions on those, we rely on visual analysis of graphs. We'll practice interpreting data with regards to level, trend, and variability in later modules. In general, though, keep in mind that visual analysis of the same data can look different on different graphs. In addition to visual analysis, an important part of behavior analysis is that rather than averaging data across individuals, we focus on the behavior of each client or participant independently. So, for example, we don't compare the average of an experimental group to the average of a control group. Averaging across sessions for an individual's data is problematic as well. In the case represented in the top graph here, it might appear based on the bar graph that behavior changed as a function of the treatment that we implemented. The average increased from baseline to intervention. However, when we look at the line graph, that removes the averaging across sessions. We see now that behavior was already increasing in count or rate before we started treatment. So how could we say that the change was because of the treatment? These visual analyses are an integral part of our science. We'll practice graphing data in Excel in later modules when we begin to talk about the different types of single-subject experimental designs. When we intervene upon behavior targeted for increase, one goal that we're often aiming for is fluency. Fluency in behavior analysis is defined specifically as that combination of accuracy plus speed of responding that enables competent individuals to function efficiently and effectively in their natural environment. We'll often set a fluency aim as a goal. For example, your goal of how many correct responses to SAFMEDS cards to reach per timing or per minute by the end of the term. This fluency should also lead naturally to outcomes including retention, maintenance, endurance, and application of component skills to composite behaviors. Just as rate of responding is the most common and sensitive measure of behavior use in our field, the translation of that into high rate and accuracy in applied settings allows for excellent measure of clients' progress. Acceleration is a great way to assess progress toward fluency, as it is a measure of change in learning over time. For example, change in the rate of responses to SAFMEDS cards over the course of a week. Has your rate of correct responding accelerated or decelerated? Hopefully the former. And how quickly has that acceleration occurred? All line graphs can display acceleration, but the standard acceleration chart, or SCC, has some benefits over a standard Excel graph, which we'll discuss shortly. As part of this course, you'll be asked to chart your own performance with SAFMEDS cards, as well as other behaviors. See the description for the upcoming Fieldwork Record C for an example. The Standard Acceleration Chart, or SCC, is new to many outside of behavior analysis, and is not universally used even by behavior analysts. We find it valuable to introduce to you as a tool that may be useful during development of your thesis, charting behavior in applied settings, or for personal projects. Here are some features of the SCC. One of the chart's primary benefits is that it is standardized. This means that anyone who has learned to use and read the chart will be able, at a glance, to interpret data displayed on another person's chart. In addition, visual presentation of data cannot be manipulated by changing the size or scale of the graph. Another feature is the calendar scale along the x-axis. This allows you to assess whether variables related to, for example, day of the week may be influencing behavior. A behavior might be more or less likely to occur, for example, on a weekend, during holidays, or following significant life events. Any anomalies would allow you to look into those changes in greater detail. The calendar scale also allows you to determine whether there have been any unusual breaks between assessment of the target behavior. The SCC has a multiply-divide scale along the y-axis. The proposal is that an improvement from 1 per minute to 10 per minute is relatively equivalent to an improvement from 10 per minute to 100 per minute, and as such should be represented as a constant linear acceleration rather than a curve. The SCC can display the full range of possible rates of human behavior, that is, from about 1 per day to 1,000 per minute. Finally, the SCC allows projection of acceleration lines to predict future behavior. By graphing along this semi-logarithmic multiply-divide scale, learning curves become straight lines, as mentioned earlier, allowing easier analysis of how and at what rate behavior will change in the future. Now we'll review some specific components of the SCC. In the location circled here at the top, you'll note the date of the Sunday prior to your first instance of data collection. The darker blue vertical lines, indicated with red arrows at the bottom, each represent a Sunday, the start of each week. Subsequent lighter blue lines are successive days of the week, Monday through Saturday. Along the top of the chart, you can see the total number of successive calendar weeks, and at the bottom of the chart, you can also see a count of the total number of successive calendar days since that first Sunday. As noted previously, the y-axis is a multiply-divide scale, meaning that the number 1 appears equidistant from the number 10, and 10 from 100, and 100 from 1,000, etc. The solid blue horizontal lines are labeled in cycles, 1, 5, and 10, then 10, 50, and 100, etc. The lines between those labeled lines increase by 1s and then by 10s, respectively. So the line directly above 1 represents 2. The line directly above 10 represents 20, and the line directly above 100 represents 200. The numbers on the y-axis of this chart represent the count per minute. Here are a couple of graphs that demonstrate potential pitfalls of traditional line graphs that use add-subtract scales. The problems primarily arise when you attempt to visually compare results across graphs with different scales. In this case, unless you look carefully, it would appear that the behaviors represented on the two graphs are changing in essentially the same ways. However, it's difficult to really judge the severity of the change. These differences in scale are more visually apparent on the SCC, and the scale is consistent, preventing any ambiguity. The same data are represented on the right on an SCC. The first batch of data corresponds to the top graph on the left, and the second batch to the bottom graph on the left. Another problem with non-standard graphs arises here. While these graphs each show the same changes in behavior, the varying scales and proportions of the graphs drastically skew visual interpretation. This can absolutely be avoided in Excel graphs, but the SCC does have the benefit of addressing the problem automatically. The same data are represented on an SCC on the right and will always look exactly the same on all SCCs. Now let's discuss the second y-axis on the right. This allows measurement of your counting times, or how long each instance of data collection was. For example, if you always use 1-minute timings, you'd consistently mark a dashed line along the 1-minute line. If you were to collect data during 5-minute sessions, you would mark the dotted line there, as shown on the right side of the chart. If data were collected in a different amount of time each session, you'd use what is called a floating time bar, with a little dash at the appropriate horizontal line on each different day. When you're using something other than a 1-minute timing, that's where a frequency finder, as described by White 2003, comes in handy. However, you can also determine how to chart your data mathematically. We'll practice with both methods in class. Let's go with the 10-minute timing to make the math easier to start out. You noted that your client said the word please 10 times during the 10-minute session. You would not mark a dot at 10 in this case. That would imply that the rate of behavior was 10 per minute. Instead, you would determine what the average count per minute was across the 10-minute session. 10 instances of behavior divided by 10 minutes equals 1. So, you would mark a dot at 1 as shown on the chart. You always divide the count of the behavior by the total number of minutes of the observation. Keep in mind that if you observe, for example, for a minute and 30 seconds, you divide by 1.5, because 30 seconds is half of a minute. You can see that the distance of the data point from the time bar changes proportionally. If 10 instances of the behavior occurred during a 1-minute session, the data would look very similar, just moved up based on the 1-minute time floor. This is represented on the right side of the chart. As suggested earlier, there are very likely to be cases in which you're not collecting data for the same amount of time each day. In this case, you'll need to use the floating time bar. During each day of data collection, you'll mark a small dash at the level corresponding to the counting time. In the case represented on this chart, on the first day of data collection, I observed for 1 minute, on the second, 2 minutes, on the third, 5, and on the last, 30 seconds. The count of behavior on each day was 20, 40, 75, and 15. This converts into rates per minute of 20, 20, 15, and 30, and those are the horizontal lines on which I charted each data point. In the case of the rate per minute of 15, you can see that the data point does not fall on one of the solid blue lines. Instead, you must estimate the difference between the labeled 10 line and the next line up, representing 20. It becomes clear in this example that an improvement from 15 to 20 per minute is considered to be relatively equivalent to an improvement from 20 to 30. On this type of chart, improvements are visually standardized and adjusted relative to this multiply-divide scale, ensuring that they aren't over-exaggerated or underrepresented. Note that you should connect your data points across days. I'm not doing so here in order for the components of the chart to be more visually clear. There are some exceptions. You shouldn't collect data points across phase change lines, nor across days when the behavior had no chance to occur. We'll discuss this more in the workshop. Here's an example of connection of data points with no connection across the phase change line. Phase change lines are typically used to mark changes to interventions, but may also be used to note events such as the client's vacation or break from school, major illnesses, or other variables that you think might affect your dependent variables. Let's take a moment to practice identifying time bars. For these 4 weeks, how long was the timing conducted every day? The timing was 30 seconds in length. This one's a little tricky since it's not explicitly labeled, but give it a shot. It's 30 minutes. The labeled line just above it represents 20 minutes, and the lines moving downward toward 50 minutes are in 10-minute increments. How about this one? The very bottom of the chart represents a 24-hour timing. Another tricky one. This represents a 1-hour timing. You can see the label on the far right, even beyond the initial second y-axis labels. It is common to chart what is sometimes called a fair pair of behaviors, such that you can simultaneously show acceleration of a desirable behavior with deceleration of a behavior targeted for decrease. In this case, the behavior to increase is typically represented with a circle, while the behavior to decrease is represented with an X. Note the 2 question marks below the time bar on this chart. These represent zeros. Question marks just below the time bar are used instead of the typical data symbols because with longer timings, you may have a count per minute of less than 1, so you wouldn't want to confuse that with zeros. Sometimes people mark zeros with data points at the very bottom of the chart on the successive calendar days line. This is fine too. I personally choose the question mark method because the data are easier to take in at a glance rather than looking across the full chart, but by all means be ready to argue your own reasoning. Let's practice reading rates charted on the SCC. What is the rate per minute here? This shows 60 per minute. And here? 10 per minute. Another one? 4 per minute. Now let's review the process of calculating the accelerations themselves. Per Binder in 1996, a trend that doubles a behavior frequency in a week is called a ×2 acceleration per week, and one that divides average frequency by 3 in a week is called a /3 acceleration. Times 1 is a flat line. This is from page 167. The first diagonal line shown here is acceleration of times 2, again showing an increase in rate from 1 per minute on the first Sunday to 2 per minute on the next to 4 per minute on the third, so the rate is doubled times 2 every week. Each individual data point represents a change in level of performance session by session. Accelerations show changes in rates of learning over time. The second diagonal line shows an increase in acceleration to times 4. Rate increases from 4 per minute to 16 per minute the next week to 64 per minute the final week. The exact numerical accelerations aren't as important as the visual analysis of a high rate of progress toward your client's goals. Data points, of course, do not always fall along a straight line, and even if they're close, may not multiply in rate by a perfect whole number. Those who regularly use the SCC often look for an improvement in behavior of about times 2 for behaviors targeted for increase, or /2 for behaviors targeted for decrease. If behavior does not improve at all or worsens across 2 observations in a row, a change to the intervention should absolutely be considered. For that matter, a change to the intervention may be warranted if progress isn't being made at a fast enough pace. For example, if it falls below the desired acceleration line across 2 observations in a row. Your client's time with you is valuable. An improvement of an acceleration of only times 1.4 could be enhanced by a more efficient intervention. Regular visual analysis of data in this way allows you to make decisions quickly. There is another symbol that's almost always added to an SCC, the aim of an intervention. To what rate do you want to increase a desirable behavior or decrease an undesirable behavior, and by what date? Remember that this is an important part of a behavior analytic goal. The point of the A should be along the vertical line representing the goal date, and the cross of the A should be along the horizontal line representing the goal rate. These markers allow you to easily visually judge whether current accelerations will allow your client to meet the goal on time. The aims here indicate a goal of at least 50 correct responses per minute and no more than 2 incorrect responses per minute. The SCC is most commonly used to chart rates of responding, but it can also accommodate charting of durations and latencies. In those cases, different symbols are typically used, often diagonal slashes. For durations of time, data points are charted based on the right y-axis. In the first case represented here, the target behavior took place during 10 seconds of a 1-minute timing. The second data point shows a duration of 30 seconds during the 1-minute timing. You can see that the data points actually descend the chart as durations increase. They approach the time floor, which would indicate the behavior taking place during the entire timing. You won't be required to do this as part of this class, but by all means consult with a professor if you'd like to learn more. Finally, let's take a quick look at all of these blanks at the bottom. The performer blank of your chart is for the name of the person whose behavior is being charted. The charter's blank is for the name of the person who is recording the behavior. Since more than one person might be recording the behavior, there is more than one blank. The counter blank is for the name of the person who counted the behavior and recorded the raw data, if that person is different than the charter. Under timer, you would write the name of the person timing the data collection, often the same as the counter, but not always. In the manager blank, you would put the name of the program manager, someone who is essentially in charge of database decisions for the learner's interventions, though this might also be the same as the charter. You will, for example, manage your own charting of your SAFMEDS card performance. Advisor and supervisor are also often the same person. It's split up simply in case of different tiers of management in different organizations. The setting details go in the blanks in the bottom left. Finally, in the counted blank, briefly summarize what behaviors you're charting and put the symbols you use to represent them right next to them. For the purposes of this class, we'll always be using what is called a daily per minute chart, but there are many other options out there as well. Here, from left to right, are a weekly per minute chart, a weekly per week chart, a daily per day chart, and a yearly per decade chart. I encourage you to think of target behaviors or events that would benefit from being charted in this way. Now on to the experimental article assigned for this module. What you've reviewed thus far about defining behavior and measuring it allows for an in-depth review of an empirical study from the field of behavior analysis. In development of your thesis, if you're writing one, a great first place to look for inspiration is research that has come before and leaves questions unanswered. The Journal of Applied Behavior Analysis is an excellent source for that, and full-text articles can be found for free online and through the library databases. We'll first review some key points regarding measurement and definition of behaviors from this article, and then move on to an example of summarizing key points of an empirical article in general. Many descriptive studies outside the field of behavior analysis use terminology that may not be as objective or measurable as our field requires. For example, with reference to inference or interpretations in the form of statements about behavior. As the authors note, final data in the form of running narrations cannot readily be transformed into units. That is, we can't visually analyze those types of data. Here are some examples from the article that include statements that we want to avoid if at all possible. Can you identify why? Jimmy is a rejected child. This statement refers to environmental events that are not immediately observable and are not objectively defined. This is an extremely aggressive child who is always getting into trouble. The description of the target behaviors here are not sufficiently objective. The preschool child makes errors in describing the water line in a jar because of his underdeveloped cognitive structure. This statement makes reference to a hypothetical construct, a cognitive structure, that cannot be observed. The fact that these statements about behavior can be made objectively is part of the first assumption stated by the authors of this article, that psychology can be a natural science. The second assumption stated in this article is that concepts and laws in psychology are derived from raw data. This type of science was described in a previous module. Do you remember the term for it? Since we base conclusions on data rather than forming hypotheses and then testing them, we are primarily an inductive science. The authors summarized that descriptive studies do not provide information on the functional properties of the events or the functional relationships of events. In summary, this statement means that correlation does not equal causation. Describing behaviors or events, even when they co-occur with other events, does not allow us to interpret whether one event caused the other. The authors review several goals of descriptive studies of behavior. Note that these goals also apply to experimental studies. First, technologically describe the setting such that it can be replicated in future studies, in the hopes that similar results can also be replicated. Next, operationally define and describe behaviors and events in observable terms. This has been the focus of our modules up to this point. As you see in this article, it's been a priority of our fields for decades. Record behavior and events. In future modules, we'll go into detail regarding different data collection methods. To give you a sneak preview, this article makes reference to event recording, partial interval recording, and whole interval recording. With regards to the final bullet points here, we'll go into detail on these topics in future modules. When it comes to IOA, just keep in mind that increasing the believability of your data by having multiple people observe and record an event does not necessarily mean that accuracy or reliability are also increased. In the case of interpretation of data, visual analysis is key. And when you analyze and judge the implications of data, interpretations would usually consist of a discussion of what was found in the situation with comparison to other findings obtained under functionally similar situations, from page 185. Now we'll move on to the empirical study portion of the assigned article. One way to make your way through empirical articles is to be on the lookout for information that contributes directly to description of each of these bullet points. When summarizing an article for your thesis, these points are very important to cover so that it is clear how the given article relates to the research that you're proposing. We will not be reviewing every assigned article in this much detail, but we will go step by step in this case to give you a place to start. A study's experimental question is typically phrased as, what is the effect of the independent variable on the dependent variable? with the dependent variable being a behavior and the independent variable being an environmental event that you manipulate as the experimenter. In this case, there was not an explicitly manipulated independent variable. Instead, the author simply observed various dependent variables in the natural environment as part of a descriptive study. How much demographic information you provide as part of a summary can vary. Ask yourself what impact the demographic information might have on interpretation of the results. If a study was conducted with only women or only men, could the results still be generalizable to individuals of other genders? If the study is conducted with one child with autism, would the results be likely to be replicable with other children with that diagnosis, or typically developing peers? This study reports the participants' IQ and results on the Wide Range Achievement Test. In general, it's preferable to report assessment results that relate directly to the dependent variables you intend to target. These test results do not directly indicate any particular behavioral repertoire. However, it can be important to write to your audience as well. Providing these test results may help an audience from other fields of psychology compare the results of this study to others from their fields. Again, the dependent variables in our field are almost universally behaviors. These are the summaries provided by the authors in text. They also very helpfully provide more detailed operational definitions in Table 3. These, however, would likely not need to be stated in detail in an article summary unless you intended to measure precisely the same behaviors in your own study. Again, we'll review partial interval recording later, especially in comparison with other data collection techniques. But this description gets the point across. Every 10 seconds, the teacher recorded the occurrence or non-occurrence of events defined in the code. Again, no variables were explicitly manipulated in this study. Instead, the dependent variables were observed over times in which environmental variables change naturally according to the daily schedule. In this case, since there were no independent variables manipulated, nothing about the implementation of an intervention needs to be described. The observation and recording techniques were essentially the method in and of themselves. Results should always be summarized with reference to numerical change over time, ideally with regard to changes in level, trend, and variability. In this study, the authors primarily compared values of the dependent variables across different changes in the environment, specifically different classroom activities. These are the numerical values that are reported in text. All values represent the average percent of intervals in which each of these behaviors occurred across sessions of each activity. You can see that the authors did not explicitly note the values for every behavior during every activity. You could estimate those values based on the graphs provided in the articles. The graphs also provide session-by-session data rather than the averages presented here. How you wanted to summarize these data would depend on how you were comparing them to your plans for your own study. Ultimately, rates of change in social interactions and sustained activity across school periods were able to be objectively displayed. Specifically, the authors note that the participant talked more than he listened, and over the period of the study, his verbal output increased, from page 190. If it was desirable for these behaviors to be intervened upon in any way, whether to increase or decrease their future rate, this descriptive study might also suggest environmental variables to which the behaviors are sensitive. In addition, the authors noted that the participants' behavior became more variable during the second half of the study. Was this due to maturation, skill development explicitly targeting in the classroom, decreased sensitivity to the outside observers who were part of the study? Manipulation of variables during an experimental study could tell you more in the future. The authors also noted some potential uses for the data collected as part of this study, listed here. Those are the steps of summarizing an empirical article. Focus on the experimental question, setting, materials, and participants, dependent variable and how that dependent variable is measured, independent variable and the methods of manipulating that independent variable, the results, and the implications.